Yes.
I wrote it here. How I got the answer.
Show it to me after class.
Okay.
Yep, yep. Other questions? All right. The last time we started talking about polynomials, we're going to do an in-depth dive into polynomials in this chapter, and then finish it off with a discussion of rational functions at the end of the chapter. So we did some of the definitions last time of what we mean by degree, what we mean by the coefficients, the constant term, what a leading coefficient is, what a leading term is, and then identify those in a particular example. We did right at the end of class last time. Being able to identify these, pardon me, goodness. Being able to identify these will help us with the concept of end behavior. Well, part of this, I should say, will help us with the concept of end behavior. So let's talk about what we mean by end behavior. Notice we got this funky looking notation here. We've got an X, and we've got this arrow, and then we've got infinity over on the side. When we're talking about this graphically, what we really mean is we're looking at the X values, and we're letting them get bigger and bigger in the positive direction. That's what this notation means. Okay? So when we write that notation, we mean X is getting large in the positive direction. Or if we think about graphically, we're moving to the right. So what do you think the next notation means with that X and an arrow and a negative infinity?
So it's going to be smaller or
Yeah.
large negative.
Yeah, so we're getting really, really large in the negative direction, and we're moving to the left. That's exactly right. Good. So X is getting large in the negative direction. So a large negative number. All right, so or we're moving to the left. Okay. All right, so we're just trying to set some notation. And then we'll do some examples here. So remember that we had all of those power functions at the beginning, near the beginning of the semester. We talked about x squared, we talked about x cubed, we talked about x to the fourth, and so on, right? We had x squared. What is its shape? X squared shape is, it's a U shape, right? It goes this way. X cubed is that S shape, it goes that way, right? At least hopefully U it's that way. For me it's backward. Right? X to the fourth. Yeah, U shape, right? X to the fifth. S shape, X to the sixth. U shape, X to the seventh, S shape, right? Just keep moving my arm this way, right? Okay. Notice that what we're talking about with end behavior is that idea of the shape at the ends, right? U shape or an S shape, or a U shape or an S shape, right? Okay. So the end behavior means what happens to the Y values what happens to the Y values as X goes to infinity and as X goes to minus infinity. What we're interested in for polynomials is which way are my tails pointing? I like to call those the tails. Are they both pointing up? Is one pointing up and one pointing down? And has it been flipped upside down? Are they both pointing down or going this way? Some really bad robot dance, if you will. Okay. All right. So that's what we mean by end behavior. Now let's think about what happens, which piece we need to look at if we're looking at end behavior. So for example, Hope taught about quadratic functions the other day. been a day or two, but Hope taught about them the other day, all right? So if you had something that looked like f of x equals 2x squared minus x minus 5, say, doesn't matter what it is, how do you know whether that parabola is pointing up or down? What told you? Yes.
The negative or positive in front of the coefficient of the x squared.
Yeah, it was this one right here, right? You looked at the x squared term, right? And you looked at the coefficient out in front and decided whether it was positive or negative, didn't you? So this one, which way would the tails point, up or down? Up, because it was positive, right? So notice that you went to the highest degree term and then looked at the coefficient, right? And again, that's telling you whether it's going this way or this way, right? Positive it goes this way, negative it goes that way, right? Okay? That's what we mean by looking at the end behavior. Which way are those tails pointing? Where did you go? You went to that highest degree term, the x squared term, and looked at the coefficient. Well, in particular, we're looking at the leading term. So when you do end behavior, the term that we're interested in is that leading term. Okay? The one that has the highest degree on it. All right. So let's make a summary table here and see if we can figure out what happens if for your end behavior depending on that leading term. All right. So let's say let's write the polynomial here for a second. If I have f of x equals a sub n x to the n, a sub n minus 1, x to the n minus 1, all the way out to a naught. The way I have that written, which one's the leading term? Yeah, it's that one as the leading term, right? So again, when you're looking at end behavior, first thing you're going to do is pick out that highest degree term, that part, right? Okay. All right. So that's going to determine completely what's happening on the ends. And that's exactly what you did with the quadratic ones, right? You went to the x squared term, looked at the coefficient. It's exactly what we're going to do here. We're just going to use symbols rather than numbers. So again, you told me x squared looks like this, x cubed looks like this, even, odd, even, odd, even, odd, right? So part of what we're going to look at is if n is even or n is odd, okay? That's one thing. Is the degree even? Is the degree odd? Remember, n here would be the degree, right? Degree even, degree odd, right? Okay. Quadratic functions, the degree was even. The next thing you looked at for quadratic functions was that coefficient in front, right? That leading coefficient. Positive or negative, right? So that's the other part you're going to look at. Your a sub n is greater than 0, or your a sub n is less than 0. Okay. All right. So it's going to be one of these four possibilities, okay? You just told me a little bit ago, if the degree is even, if it's an x squared or an x fourth or x to the 6th or x to the 8th, so on, the tails both point in the same direction, correct? Okay. If the coefficient happens to be negative, what would the negative coefficient do? Instead of both of them pointing up, it would both point down, right? Okay. So we're going to write this in math speak with the end behavior and then think about what the picture looks like, okay? So end behavior, we're going to write it as two statements. As x goes to infinity, f of x goes to something, and then the other way, okay? F of x goes to something, okay? And I'm going to fill in the blanks here in a second, all right? But again, remember, this notation basically says as you go to the right, the y's do something. As you go to the left, the y's do something. That's what that is what it is, right? But you just told me that if it's something like x squared, whether I go to the right or go to the left, which way does the function point? Up, right? So as x gets bigger, either way, the y's get bigger. They go off to infinity, right? Okay. So both of these would be filled out with infinity. And again, in words, what does this say? You go to the right, the graph goes up. You go to the left, the graph still goes up. That's what that says. Okay? The as x goes to infinity part is saying it goes to the right. The as x goes to negative infinity part is saying it goes to the left. Right? And if you think about x squared, doesn't matter, they both go up. Okay? So they both go to positive infinity. What happens if you multiply by a negative in front? Instead of them both going up, what would happen? They both go down. Good. So this would be f of x goes to negative infinity. As x goes to negative infinity, f of x goes to negative infinity. So from a graphical standpoint, all this is telling me is what's going on the ends. It doesn't tell me anything about what happens in the middle. Okay? So in the first case, you know what points up on the left, you know what points up on the right, but I don't know what happens in the middle. So I'm just going to fill that in with dots because there might be some bumps in there. There may not be some bumps, but there might be some bumps. Okay? So that's why I have the dots in there. I just don't know what happens in the middle. We're going to have a little bit of information when we gather some more information. We'll have a little bit more information. But if you really want to get down to the nitty-gritty of what happens in the middle, you take calculus. Okay. We're going to do a couple of things that will allow us to give us a little bit more information. But generally speaking, if you want to analyze what's on the inside, you have to do calculus. And calculus is another name for analysis. Okay. All right. For the other picture, we're saying that both point down. So you'd have a down, and again, I don't know what happens in the middle. That makes sense? That part makes sense? Okay. What about odd? If you have something like x cubed, positive x cubed goes lower left to upper right. Right? Okay? So let's think about how we write that as end behavior. Oops. As x goes to positive infinity, f of x does something. As x goes to negative infinity, f of x does something. All right. Notice here, positive leading coefficient. So I want to think of like positive x cubed. The first statement, are we talking about x going to the right or left? To the right, right? Because this is x goes to positive infinity. As you go to the right, which way is your function point? Up. So that second statement will be as f of x goes to infinity. Yeah, so f of x goes to infinity. The second statement says as you go to the left, as you go out to the left, x cubed points down, right? So how would I finish off that statement? Negative infinity. Good. Okay. So again, if I think about a picture, left tail points down, right tail points up. No idea what happens in the middle based on leading term. What happens if you change your leading coefficient to be negative? What happens to your picture if your leading coefficient is negative? Instead of going this way, what happens? It flips, right? It flips upside down, right? We've talked about doing those transformations, right? When you multiply by a negative, flips it upside down. Okay. So as x goes to the right, which way is the function going, up or down now? Down. So we would write negative infinity. As you go to the left, which way is the function pointing, up or down? Up. So it's going to go to infinity. And so again, if you think about a picture, it looks like that. So this table summarizes your end behavior for you. But again, I think it's just as easy to remember x squared, x cubed, right? Even looks like x squared, so they both point in the same direction. Odd looks like x cubed, they point in opposite directions. And then you just have to use your negative sign to determine whether it's flipped upside down. All right. So let's see if we can put that to use. This one asks us to determine the end behavior of negative 4x cubed minus 7x squared plus 12x minus 5. What is the term that matters?
First.
Yeah, the x cubed, right? This is your leading term. For end behavior, that's what matters. Okay? Is the degree even or odd? Odd, right? So do the tails point the same direction or do the tails point in the opposite direction? Opposite. Good. Okay. I'll write that off. You don't have to write this off every time. But write this down every time, but I'm going to. Degree odd, your tails point opposite directions. You have a question? Oh, okay. All right. So if we want to write the end behavior, then we make those two statements. As x goes to positive infinity, f of x goes somewhere. As x goes to negative infinity, f of x goes to somewhere. You already told me they point opposite directions. So it either has to go lower left to upper right or vice versa. Which is it? Is it lower left to upper right or upper left to lower right? Upper left to lower right because of what? The negative sign, right? That negative sign right here tells you you've basically taken your x cubed and flipped it upside down. Okay? So that means as you go to the right, the function goes which way? Down. So it goes to negative infinity. And the other one must be positive infinity. Questions on that one? Okay. Work on the next one for a second. Well, I'll give you 2 seconds. How's that sound? Okay. Work on it for a minute. We'll chat about it. Yeah.
When it comes to like formatting these like answers, like the work isn't always like answers are more like obvious. So would it be easier to?
I want you to write it using the notation. So that as x goes to infinity, f of x. Yeah, that's how I want you to write your answers. Yep. Ready to talk about it? Which term matters?
12x to the power 6.
Okay, 12x to the 6th. The degree is it's even, right? Yep. So does that what does that tell you about the tails? Same direction, right? Even degree is same direction, correct? Now, which is it? Both up or both down? Both up. What tells you that? The positive 12, right? Okay. So degree even, just write that down. Degree even, tails point same way, same direction. Positive leading coefficient. If I can spell coefficient, that would be helpful. There we go. Both point down. Okay, cool. So again, we want to write this in our end behavior speak. As x goes to infinity, f of x goes to, or they both point up, sorry. We go to infinity. And as x goes to negative infinity, f of x also goes to infinity. Is that what we got for our answers? Not too bad, I hope. It's one of 4 cases, right? You gotta keep the 4 cases straight, but it's one of 4. There's nothing any more that's literally as complicated as this gets. Okay? All right. I know, it's going to get worse. Sorry. But the end behavior is that straightforward. It's not going to get too bad. It's just not as straightforward as the end behavior necessarily. All right. What we're going to be concentrating on for a good chunk of the rest of this chapter is figuring out figuring out zeros of polynomials. The idea behind that is we're looking really to try to solve equations. One of the things that you do when you solve quadratic equations, for example, is you set them equal to 0 and factor, right? One of the ways you solve quadratic equations is set them equal to 0 and factor. What you're looking for are the zeros of a quadratic. That's what we mean by a zero. Okay? So what we mean by a zero of a polynomial means that if you plug the number into the polynomial, you get 0 out. That's what it means to be a zero. Okay? There are other ways to say 0, and one of the ways is a word that I will use interchangeably. One of them is that we also say C is a root of the polynomial. Root and 0 for polynomials mean the same thing. The square root of 0 is 0, yes. All right. So C as a root is one way to say it. Another way to say it, pardon me, is that C is a solution to the equation f of x equals 0. That's another way to say it. If you think about one of the ways that you solve quadratic equations is by factoring, we might also say that x minus c is a factor of f of x, and we're going to spend some time later in this chapter doing a lot of factoring. And then the last thing is a graphical thing, and it says that the point c comma 0 is an x-intercept of the graph of y equals f of x. And this is what the word root means in this case. If you think about the x-axis as being kind of a ground level, the x-intercepts would be where it's rooted. That's what where the word root comes from on that. Okay. All right. The only reason why I went through those is because those all just mean the same thing. So if you see a problem that's asking you one of those things, it's basically asking you find the zeros. All right. This first one, I made a typo here, or I've lost a term somewhere, but I want to make this a little bit easier. Change the x cubed to an x squared and the x squared to an x. Makes the problem a lot easier. Okay, so change the cubed to a squared, change the squared to just a first power. So it should be negative 5x squared plus 10x plus 75. All right. So if we want to find the zeros, all that means is try to solve it. Set it equal to 0. We have a quadratic here. Our main technique for trying to solve quadratic equations is to factor. Do you see a common factor that you can pull out? 5. In fact, I can pull out a negative 5. Make it a little bit easier. If I pull out the negative, your first term is just an x squared. If I pull out the negative, what's the second term? Yeah, minus 2x. Pull out a negative out of the 75. I think it's minus 15, isn't it? Yeah. Do you see how that polynomial factors, that quadratic factors? Yeah, that's right. X minus 5 and an x plus 3. Good. Okay. And now again, to find your zeros, to find your roots, find your solutions, I would set each piece equal to 0. Can that be 0? Can negative 5 equal 0? No. Okay, so that one doesn't give you anything. When is this one equal to 0? at 5, good, right? X equals 5. This one will be negative 3, good. If you need to, write x minus 5 equals 0 and add your 5. Write x plus 3 equals 0 and subtract your 3. All right, so these would be your zeros. All right. So the next one asks us to use the end behavior and zeros to sketch a graph. Okay, well, let's do the end behavior first because we already did that. Which term do you look at for end behavior? Highest degree term. So in this case, it's the negative x cubed term, right? That's the one we're interested in. Same direction, opposite direction for the tails. Opposite. Does it do lower left to upper right or vice versa? Vice versa. It goes the other way, all right? Why does it go the other way? What's telling you that it's upper left or lower right? The negative sign, right? Okay? So let's write the end behavior. As you go to the right, as x goes to positive infinity, f of x goes to negative infinity. Good. As x goes to the left, as you go to negative infinity, f of x goes to positive infinity. Good. Everybody okay with the end behavior? Writing it that way? Because you'll have to put your answers like this in WebAssign, and I'll expect your answers like this on the exam too. So, okay. So far, so good? Okay. Let's do zeros. One of the reasons why I wanted to do this one was just to remind us of a factoring technique. When we got a 4-term polynomial, the only way we really have to factor is by grouping. Okay? So let's look at the first two and the last two. If you look at the first two terms, what can you pull out?
Negative x squared.
A negative x squared. When you pull out a negative x squared, you're left with x plus 2. Good. Oh, yep. It should be a minus. Yep.
Oh, no.
Yep, because I pulled out the minus sign. Because we pulled out the minus sign. It should be an x minus 2. Isn't it? No.
You put a line through that.
Oh, I got a line through it. My bad. That should be a plus. That was me. Sorry. It looked like a plus because I put the circle through it. My apologies. Yeah, it should be a plus. You're right. We're going to have an issue here in a second. All right, looking at the second two terms, what can you pull out? A 9. You're left with x plus 2. I would have realized something was goofy here in a second because these have to match if you're going to do factor by grouping. Okay. Pull out your x plus 2. What are you left with?
Negative x.
Good. So you pull out the x plus 2, you're left with negative x squared plus 9. That can factor a little bit more, especially if I write it as 9 minus x squared. Do you recognize how that factors?
Yep.
It's a difference of squares, so you can write it as what? So it'll be flipped around. Since I got the 9 first, it'll be flipped around, right? So it'll be 3 minus x and 3 plus x. What makes the first factor equal to 0? And the second one? And the next one? Good. So there are our zeros. Okay. We'll do this off to the side. Are we okay with the zeros? Okay. All right. So the problem also asks us to sketch a graph. So the zeros, again, are where the graph, and I'm not going to worry about scale in the y direction, by the way, just the x. Negative 3, negative 2, and 3. Those zeros tell us, again, where the function crosses the x-axis, right, or touches the x-axis. It may not necessarily cross. We'll talk about that in a second. But remember, each zero corresponds to an x-intercept. Right? We agree? Okay. Then we can also use our end behavior. where if I wanted to start drawing this, it either has to start up here or down here. But what'd you say the end behavior was? Was it upper left or lower left? It was upper, right? So I would come down. I'm going to cross through -3. I'll come back up through -2. All right. I'll come back around through 3. And notice that I'm pointing down. Is that good? Yeah. There's a rough sketch. Very rough. Again, I'm not worried about perfection at all. Just looking for a sketch. We could have got one more point on this graph. How would I have figured out where this crosses the y-axis? How do you figure out what's the x-coordinate of any point on the y-axis? Say it again? Why is it plus 18? You're right. Okay. So it works kind of the same way. What's the x-coordinate on any point on the y-axis? If I'm on the y-axis, how far left or right did you go?
0.
0. So what's the x-coordinate? 0, right? The x-coordinate is 0. So how do you find the y-coordinate if the x-coordinate is 0? Yeah, plug in 0 for x, and it kills off all those x's, right? Your y-intercept is the constant for a polynomial here. Remember we talking about what the constant is, right? The y-intercept is the constant. This would have had to cross the y-axis at 18. It's another point that we can use to help us get some information. Now, there's not much more information we're going to get about the graph on the in between the tails, but getting zeros and y-intercept helps. Okay, gives you a little bit more idea of what the graph looks like. Right. There is one more piece of information that we can get about the graph, and that's the idea of the multiplicity of a root or a multiplicity of a 0. So remember that an equivalent statement to saying c is a 0 is also that x minus c is a factor. Okay? So multiplicity has to do with the power on the factor. So we say that the 0c has a multiplicity of m if x minus c to the m is a factor of f of x. Oops. But x minus c to the m plus 1 is not. Okay. Basically, what we're saying is, if it's in factored form, you're looking for that exponent. Okay? So let's look at this example. I think this is a lot more illustrative with an example than it is with the definition. I think the definition just messes up messes it up. Messes up, makes it foggy, if you will. All right. Looking at this is factored already. Yes.
M plus what?
M plus 1. Yeah, it's the highest power that I can put on the factor. Well, yep. That's all it means. Okay. Let's look at this factored form. If you set this equal to 0, you can see the zeros. This would give you a 0 of what? Lies. Okay. If I set this equal to 0, what makes it 0? -4. This one is +1. This is +5, right? Right? Set that x plus 4 equals 0, you get -4. Set x minus 1 equal to 0, you get 1, right? Okay? So your zeros are -4, 1, and 5. If I want the multiplicities, I'm looking at the powers. So what's the multiplicity for -4? 2. -4 came from this factor, right? The one I just circled. -4 came from that factor. The power on that factor is 2. What's the multiplicity for 1 then? 3. And the multiplicity for 5 will be 1, because that'll be the power, right? Okay. All right. Multiplicities tell us what the graphs look like near where it crosses the x-axis. We're near those zeros, okay? All right, so let's think about something real quick, okay? Let's think about the graphs of y equals x squared, and y equals x cubed. What does y equal x look like? It's a line, right? Did that flatten out at all when it crossed the x-axis? No. What's y equals x squared look like? Yeah, it's a parabola. It comes down, touches the x-axis, and goes away, doesn't it? Okay. Still has an x-intercept of 0, but did it cross? No, it just kissed it, right? Just touched it and bounced back off again, didn't it? Okay. How about x cubed? What does it look like? Yeah, it's an S shape again, right? But notice that when you get close to that x-axis, it flattens, right? Okay. Does that make sense? Okay. Notice if you did an x to the 4th, it would do that kissing idea again, right? Just touch and go back up. X to the 5th is that S shape. It would do a flatten, okay? So crosses versus touches. We cross if the multiplicity is odd. And it touches if the multiplicity is even. Okay? It comes down, and if it's even, it comes down, just touches it as it goes back up again. If the multiplicity is odd, it crosses. Okay? What about the flattening? Well, looking at the 3 examples that I drew before we started, where's the only one where it doesn't flatten? Which one of those didn't it flatten at the 0? The y equals x, right? The other one's it flattens there, doesn't it? Okay? So it flattens if the multiplicity is greater than 1. Doesn't matter if it touches or crosses. If that multiplicity is greater than 1, then it flattens. Okay. All right. So let's see if we can do an example here. Lots of information. This is kind of the summary, if you will, of everything that we've talked about today. That's exciting. Okay? All right. So the first part, notice I've already got this nice and factored for you, right? So you should be able to tell me the zeros pretty easily, right? What are the zeros?
-4, -1, +3.
Yeah, -4, -1, +3, +5, right? We see those? Okay. Of all of the things that I have listed here that I'm asking you to find, what does that refer to? There's two things. It's the x-intercepts, right? Okay. So the x-intercepts here would be -4, 0, -1, 0, 3, 0, and 5, 0. Right? You should also be able to tell me the multiplicities. We just did that a minute ago. For, if I do my zeros again listed, you told me they were -4, -1, 3, and 5. If I could spell the word multiplicity, that would help. For -4, what's your multiplicity? 2. For -1, the multiplicity is 1. For 3, it's 3. And for 5, it is 1 again, right? Remember, again, for multiplicities, we're interested in the powers on the factors, right? Okay. The x plus 4 factor gave us the 0 of -4. The power on that is 2, so the multiplicity is 2. Does that make sense? Okay. All right. Let's see if we can, let's answer part G and then we'll go back up through the rest of it. Okay. Part G says the zeros at which the graph flattens. Again, The thing that tells us whether or not it flattens is if the multiplicity is greater than 1. So where does it flatten? In positive 3. Good. Doesn't matter that 1 is 2 and 1 is 3, right? It matters that they're greater than 1. That tells us flattening. Okay? All right. Let's see if we can answer the other questions. We like this in factored form because it allows us to see what the zeros are quickly. What factored form doesn't allow us necessarily to see quickly are these other answers, but then we can get to them pretty quickly. All right, so let's just think about the degree. Degree is highest degree term again, right? Okay. If I just multiplied out the x plus 4 squared, what would be your highest degree term? The squared, right? If you were to multiply out your x minus 3 cubed, what would be your highest degree term? Cubed, right? So what do you get if I take an x squared times an x times an x cubed times another x? If I take an x squared times an x, I'll get, if I take x squared times x, I get x cubed times an x cubed will give me 6, good, times another x will give me x to the 7th, right? So what will your degree be? Yeah, so the degree, this is the number, it's 7, right? Look at where that 7 came from. This one gave an x squared. That gives us an x. That gives us an x cubed. That gives us an x. All right? 2 plus 1 plus 3 plus 1. We add exponents, right? When we multiply. Okay? All right. So we get a 7 for our degree there. Okay? How about leading to coefficient? Okay, let's look at each individual factor again. That gives me a 1x squared, doesn't it, when I multiply it? That'll give me a 1x, a 1x cubed, and another 1x. What are we multiplying everything that I go out in front? Negative 3. So what's going to be your leading coefficient then? Negative 3. Good. Okay. Now we can answer the question, the end behavior question. The leading coefficient is negative. The degree is odd. Degree odd tells you what about the tails? One's up and one's down. The negative tells you it's, it's like a negative x cubed, right? Upper left to lower right. Okay? As x goes to infinity, f of x goes to... Good. As x goes to negative infinity, f of x goes to positive infinity. The last bit of information here before we graph it. What do you plug in for x to figure out your y-intercept? 0. Good. It'll be a big number, right? Put in 0 for x, we'll get 4 squared in that first factor, 1 in the second, negative 3 cubed in the third, and negative 5 in the last one. Whatever that number turns out to be. Looks like a good job for a calculator. It'll be negative, I can tell you that for sure.
6,480.
Yep, that's what I got.
Okay, call again. All right, so your y-intercept then will be at the point 0, comma negative 6480, and now we're ready to make a graph. Woohoo! All right. The important part of this word, the most important part of this, the words in this last part is a rough sketch, right? It's not going to be exact at all. Okay? All right. So I just made a scale here. I'm not going to make any vertical scale. The only point I'm going to put on my y-axis is the negative 6480 down here. All right? I'm not even going to bother writing all the other numbers on my scale. Just it's going by ones here. Where did we have zeros at? -4, -1, 3, 5. And a y-intercept down here at negative 6480. Okay? I'm going to work my way from left to right and use all the information that I have. Okay? Just need to know where to start. We start upper left or lower left? Upper left. Good. We're going to go upper left. We're going to get close to -4. Does it flatten at -4? Yes. All right. It flattens. Does it cross or kiss? Kiss, because it's even, right? So it's going to come down, touch, and go back up again. Go to -1. Do we flatten at -1? No. Does it cross or kiss? Crosses, right? Because it's odd. So we'll go straight through. Now I've got that y-intercept to go through. Come back up to 3. Does it flatten at 3? We'll do the cross in a second. Does it flatten? Yes, because we have it listed right here in front of me, don't I? Now, does it cross or does it kiss? Kiss. It crosses because it's odd, right? So it's going to flatten and go. It's going to have that snake shape there. Finally, at 5, what happens? Crosses, and does it flatten? No. So it goes straight through. Did we end up in the right place? Is it supposed to end up to the lower right? Yeah. So there's our rough sketch. Okay. All right. We'll do another example next time. All right. We'll do that next example. We'll also get into the next section on dividing polynomials. So we'll talk about those next time. Have a good one. We'll see you on Wednesday.